In this lesson, we're going to be looking at solving exponential and logarithmic equations. A little later on, we'll make use of these properties of logs that we talked about in our previous lessons. But first, let's talk about solving equations with exponential expressions in them. When we first talked about logarithmic equations, we looked at exponential equations that were nice. And what I mean by nice is that we can use some algebra to rewrite both sides of the equation in terms of the same base. An example we have here is 2 to the power 3x minus 8 equals 16. 16 is a perfect power of 2. We can rewrite 16 as 2 to the 4th power. So then we have 2 to the power 3x minus 8 equals 2 to the power 4. And since our bases are exactly the same, that's what we mean by a common base, then the exponents must be equal. So we could just try to solve 3x minus 8 equals 4. Solve that for x, and we'll find out what x is, and we'll solve our equation. And it looks like x should equal 4. If we check 2 to the power 3 times 4 minus 8, does that equal 16? 3 times 4 is 12. 12 minus 8 is 4. And 2 to the 4th power indeed equals 16. So this is what we mean by a nice exponential equation. We have the base, and then on the other side of the equation, a perfect power of that base. But that's not how the world works all the time. What if we don't have a nice exponential equation where we can rewrite the equation in terms of a common base? An example, 4 to the power x equals 15. 15's not a perfect power of 4. It's really close to 16, which is a perfect power of 4, but close doesn't cut it. So we don't have a way to rewrite it in terms of a common base. We can, however, use one of our properties of logs from the last lesson, and we can use the log property of exponents. If I have a log base b of an exponential expression, I can pull that exponent rule out front to multiply, related to our exponential rule that says if we have an exponential expression that we raise to another power, we multiply the powers. But in order to do this, in my original equation, I don't have a log at all. I need to introduce a log. Also, when we're solving equations, we use the inverse operation in order to solve. If we're adding inside an equation, we would subtract on both sides, so we're undoing that operation. If we've got, for example, a square root of x, we would square both sides to get rid of that square root. So we're using the inverse operations in order to solve. We're going to do the same thing here in these exponential functions that are not nice. We do have two different strategies we can use, and I'm going to try to break them down for you. I'm going to write 4 to the power x equals 15. So 4 to the power x equals 15. First, we could use log base 4 because it's the inverse function of 4 to the power x. So we'll use the same base as our exponential expression. Notice we have the exponential expression by itself on the left side. So we'll take log base 4 of both sides. And remember, this is just one way. I'm going to show you the other one in just a minute. When log base 4 and 4 get together, they cancel each other out because they are inverses. And we're left with x on the left. And x equals log base 4 of 15. This is what we would call an exact answer. X equals log base 4 of 15. If I want to approximate that answer, I need to put it into the calculator. But my calculator does not have log base 4. In order to get an approximate answer, I have to use the change of base formula first. So the change of base formula says that if I have log base b of x, then I can rewrite it in any other log. I put the argument in the numerator and the base, the old base, in the denominator, and I can write any log in terms of any other log. My calculator only has log base 10 and natural log, so I'm going to use log base 10. I'll do log 15 divided by log 4 to get an approximation. So on our calculator, log 15 divided by log 4. And before I hit equals, I do want to point out, since 15 is really close to 16, and 16 is 4 squared, x should be something close to 2. It's not going to be 2, it'll be less, but it should be close. This is a good way to estimate our answer and check our reasoning, check our understanding, and check our calculator, make sure that we put in the right stuff. And sure enough, 1.953, we have something close to 2, which it should be, and this is our approximation. When we get that decimal answer goes on forever and ever and ever. It's irrational. There's no way we can write it in a nice pretty fraction or in a decimal that ends, so we approximate it. 1.953, and this is called our approximate answer. So exact answer up here, approximate answer as our decimal. And that's one way we can solve exponential equations. Looking at another way to solve exponential equations, instead of using log base 4, we're going to use any log. The idea being we just want to pull that x down to the main level of the equation so that we can solve for x. So both sides of the equation, we can apply log. I'm going to do log base 10 or log base e, either one, because I know my calculator can handle that. And then once I do that, the exponent can come down front. X log 4 equals log 15. And this log 4, log 15, these are numbers. Log 4 is the exponent on 10, that would give me 4. Log 15 is the exponent on 10, that would give me 15. So I can divide by these numbers. I want to get x by itself, I can divide by log 4. Now be really careful. Log by itself is not a number. It's an operation. It's a function. So we're not able to cancel the logs out. That's not how things work. We leave them there. And the reason behind that is it's not the case that 15 divided by 4 would give me the right exponent. It doesn't. Even just doing a really quick example, 15 divided by 4 gives me 3.75. That's way higher than my 1.953 that I got with the other method. So I don't get to just divide the arguments. I'm not allowed to do that. But I do want to point out this log 15 divided by log 4. Check right back there when we did our log base 4 on both sides, and we used the change of base formula. If we use any log, we automatically get that change of base formula in there. This can be considered our exact answer, and then if we wanted to approximate it, we would plug that into the calculator, which we already did, to get the approximate 1.953. You can use either method, any generic log on both sides, or log of the appropriate base on both sides. Just remember that whatever you do to one side of the equation, you must do that same thing to the other, and you must be using the same base of logs. Otherwise, it doesn't work.